Let me share my screen to start. Make sure everything works. Okay, good. So this started, the idea to give this talk started with Visu Makam telling me that some talks are extremely technical, and he feels like maybe it's a good idea to give some high-level survey talk in this form. Yeah, and I said fine, because I like to give this kind of talks. And I actually have a talk, or actually several talks that are much more directed or related to the projects that, the GCT projects and algebraic complexity. But I think you will have heard or will discuss many of these ideas in much more detail than a survey talk. And what I suggested to Visu, to Kavitz, to talk about, and Thomas, to talk about a very related topic, but at a higher level. This is, my favorite two polynomials, everybody's favorite two polynomials, the permanent, the determinant, and tell you about their, incarnations, relations, connections, and appearances in lots of different places, and when they look similar and when they look different, and how they look different, and in particular some of their, amazing properties that make them so central in mathematics and in computer science. I'm sure that some of you will know some of what's here, or a lot, but yeah, I at least hope that most of you will not know everything. So maybe some of you, you will all find something new in this, because I'm going to cover many different aspects of these appearances of these polynomials. Of course, this, it seems like a friendly, relaxed forum, so just stop me with everything, anything you want to ask, and I'll answer. And also, it seems like it's more than an hour even allotted, right? So it's, yeah, there's plenty of time. I don't think it will take an hour, this talk. But I can elaborate on things if you want. So yeah, I don't know if any of you have seen this stupid movie, but yeah, the permanent and determinant are twins, roughly like this guy. So fix a field, it's interesting only if the characteristic is not true. We think of matrices and by matrices, and these two twins, polynomials, are the determinant and the permanent. I'm sure you all know them. So determinant is maybe the most familiar polynomial in mathematics, and the permanent is the same, has the same structure, only does not have the sign of the permutation. So it's all coefficients of 0 and 1 in this polynomial. So they look alike, they look very much alike, homogeneous, are multilinear in the matrix entries. The degree n on these n squared variables, have simple coefficients. So what do we want to do with them? Here is a slide that will tell you many aspects in which they, many points of view into these polynomials, and we'll elaborate on many of these later on, okay, in different parts of the talk. Physics, I mean, this is something that's rarely seen, rarely discussed in connections, but it's extremely important, and we'll talk about it towards the end. Somehow they appear in physics very prominently. I mean, they are the wave functions of n independent particles, and depending on whether these particles are fermions or bosons, and I'll explain this a bit later, the wave function will be either the determinant or the permanent. So they occur naturally in physics. They occur naturally in knot theory. I mean, basically the Alexander, so knot invariants are polynomials, and the Alexander polynomial, one probably the most famous knot invariant, is actually a determinant, and the much more powerful Jones polynomial is a permanent. They rarely discuss. I will not elaborate on this. I'll mention maybe now. I think that for mathematicians, it doesn't bother them that the Jones polynomial is a permanent until any of them want to actually compute it. Determinants are used really all over the place. Of course, it plays a major role in linear algebra and solving linear systems. It also appears that captures the volume of bodies in geometry. Permanent occurs mostly in enumeration problems. There are many of them in algebraic combinatorics, many in statistical mechanics. And of course, as we know and we'll see, a lot plays an absolutely major role in computational complexity. And it was central to many results, very important results in computational complexity. I mentioned counting. Both determinants and permanent counting are counting objects. And I'll talk about this a bit later. It's just that the permanent seem to count many more things. Basically, everything we are interested in, the permanent counts. The determinant counts as a very special type of structures, like spanning trees and planar matchings. And from the complexity point of view, the determinant is an easy to compute polynomial. We all know how to do that. And the permanent, it's a great open question. Is it as difficult as it seems? And we'll see evidence why it should be. Part of this evidence is that, and part of the importance of this polynomial is that they are complete. They are complete objects, both in Boolean classes and in arithmetic classes. In Boolean classes, determinant sort of complete for NC, for fast parallel computation, and the permanent is complete for the general counting problems. I'll elaborate. And in the arithmetic setting, they capture the variance classes, the VP and VNP, which we'll define. These yellow balloons just highlight that these objects appear really all over the place. And it's not surprising that they are complete from this point of view. Okay, so let's see where they stand relative to well-known complexity classes as we understand them today. I mean, we have no collapses of complexity classes. So we start with the standard dichotomy that we know and love between P and NP. We believe that well, P are the things we can easily compute, and NP are those that we can easily verify, but believe that it's hard to compute. And they are not quite, determinant seems to me quite a bit below P, and permanent quite a bit above NP. And where exactly are they? Well, this is roughly the more detailed pictures of complexity classes. I'm not sure that all of you know all these classes. All are natural, capture natural resource bounds. And as I mentioned before, the permanent is complete for a class called Charpy that I'll define, a class of natural counting problems. And the determinant is complete for those computations that can be done efficiently also in parallel. There's another class that seems to will enter the picture, which is recent, those problems that can be solved quickly on a quantum computer. And it turns out that it's sort of, did I erase this line? It's somewhere under Charpy. So it's sort of reducible to permanent, which is very interesting. And the variance completeness results, I mentioned them in the Boolean setting. In the arithmetic setting, they are complete for these classes. As I said, I'll talk about it later. So that's roughly where they are in this in our world of complexity classes. Let me start from arithmetic computation. We see this picture again at the end, but anyway, just to put everybody on the same page, what is I'll talk about arithmetic complexity for a while, and then I'll move to Boolean complexity. In arithmetic complexity, we have notions of natural notions of computations of circuits and formulas. These are circuits, and these are formulas. The only difference is that in a formula, you cannot combine results. So a formula is a tree, whereas a circuit is really a directed acyclic graph. You start from the variables, which are from the inputs, which are variables, and using addition and multiplication and coefficients in your field, you are computing a polynomial. So it's about formal computation of polynomials. We always assume that the polynomials we compute have degree which is polynomially related to the number of variables. This is a basic assumption in the whole field invariance theory of arithmetic complexity. And given that, and completely in contrast to what we expect is true in the Boolean case, we have the following result that says that these two models are really very close to each other. They're almost polynomially related. In Boolean complexity, we expect them to be exponentially far apart. So in the arithmetic world, it's convenient because we can discuss either circuits or formulas, and it wouldn't matter. So that's very convenient. So sometimes I mention circuit, sometimes formula, but this is roughly the sizes are, you should think of them as comparable. And so VP, the class of problems, polynomials that are easily computable, are exactly those who have a circuit of size polynomial in it. Okay, these are things we can efficiently compute, completely analogous to the class P for Boolean computation. The V there stands for Valiant. Of course, it's not his name, but everybody calls this class VP, Valiant P. And we are trying to understand this class and soon analogous class VNP. So let me go straight to this question, which is the analog of P versus NP question in the arithmetic world. And the question is written in the bottom. Just like in P versus NP, what we are really asking is whether we can efficiently compute everything we care about. NP somehow captures everything, all decision problems we care about, or we can reasonably hope to solve efficiently. And the question is whether we can. And same thing in the arithmetic world. So here are all polynomials of some degree. You can think of degree n like the number of variables. As I said, VP is a class of easy polynomials, and it includes a determinant and many others, Fourier transforms, symmetric polynomials, matrix multiplication, many others that we can compute efficiently. And we want to know how big is this class? I mean, does it contain everything? And of course, it doesn't contain everything. A random polynomial is hard. A random polynomial will require exponential size circuits to compute. But of course, we don't want to compute random polynomials. We don't want to compute interesting polynomials. And the only question is what is interesting, and what are the polynomials we care about? And Valiant defined them. I mean, he defined the class VNP, which I'm not defining yet. But you should really think about them as those, all polynomials we care about that we can hope to maybe compute efficiently, and we really anyway love to compute. Why? Because as I mentioned before, they capture many enumeration polynomials occurring in algebraic combinatorics, for example, and many problems in statistical physics, and as I mentioned, in knot theory and many other areas of mathematics. So the question is whether these two classes are equal. And there's another important problem in the VNP class, which is a permanent, as we saw before. And what Valiant proved is that these two polynomials are complete in their respective classes. And completeness, as you all know from arithmetic or Boolean complexity theory, when you want to talk about classes of problems and whether they are equal or separate, and you have complete problems for these classes, you might as well restrict your attention to understand the relative power of these two polynomials or these two problems, and forget about classes and the computational model and so When you say complete, you need a notion of reduction between polynomials, and it's extremely elegant variant theory of arithmetic complexity that the notion of reduction is mathematically extremely elegant. You just wonder, you want to say that one polynomial is easier than another. F is at most G. The question is whether you can project linearly or finally project F to G, right? Just whether it embeds there under linear transformation. So it's a very elegant notion of reduction, and under this very elegant notion of reduction, we'll see a demonstration of affine projection in a second. These two polynomials are complete. Okay, so let's talk about more about these completeness results. But yeah, nobody's asking anything, so let me look at all of you a bit and see whether so I have your faces and see anybody wants to ask any questions, or everything clear? Too fast, too slow? Okay. No comment.
No, the only question I had was your statement about BQP. I don't know much about quantum, but the so
yeah, I'll discuss it more.
Get there. Okay.
Yeah, I'll get that. Yeah. Okay, so good. Let's continue. Okay, so let's discuss first determinant and its completeness. And so yeah, I like to ask, it's like in a live class, what's the complexity of determinant? Everybody answers a polynomial or n cube or something. And in this model of arithmetic circuits, and I ask, how do you do it? And everybody says Gauss elimination. And I ask, but Gauss elimination entails division. It entails, testing whether something is zero or not, so you don't divide by zero. This doesn't fit in the model, right? And then in most cases, there is silence. Of course, in this crowd, I'm sure most of you know that you don't require divisions to compute the determinant. I mean, it was discovered by many people. Strassen did it by division elimination, and there are very direct methods that were known, Samuelson, and then later Sansky and Berkowitz. And there are many ways to compute the determinant. It's a polynomial, right? So you don't expect to use division. In fact, you don't need to use division. Strassen's result is that, in general, if you have an arithmetic circuit with division computing a polynomial, you can remove the division without blowing up the circuit by much, and have an arithmetic circuit without division computing the same polynomial. So it's a general result. So okay, so determinant is certainly easy, as we said, it's in VP. The formula, I mentioned that they are close, but this is a demonstration just how close or how far they are. The best formula we have for determinant is slightly super polynomial, n to the log n, and I'll mention many open questions that I hope, some of them have been open for decades. Maybe in this project of yours, or anybody interested will think about them and make progress on them. It's a great open question of whether there's a polynomial size formula for the determinant. I'm not sure even what I believe. And the main result I want to present here in this slide is the variance result. So what is variance result? It says that the determinant is complete for VP. So I'll state it now, ambiguating formulas and circuits. Let me talk about formulas. Suppose that F has a formula. Remember my notation, L is the formula size. Suppose that some polynomial F has a formula of size S. Then you can affinely project it to a 2s by 2s determinant. In other words, you can create a matrix, which is just the same, essentially the same size as your formula. The entries will be just, affine forms. In fact, they'll be just either variables or constants, such that the determinant of this matrix is your polynomial. Okay, so any polynomial is a determinant of the same, with the same, roughly the same size of the formula, computing it. And I love this proof of Valiant. There are other proofs, well, not too many, but because it fits on one slide and because it's, you know, maybe demonstrates, you know, both how powerful determinant is and, you know, how more general mathematically, how clever you need to be in proving things by induction sometimes where you think that it will be extremely easy. So yeah, I'm just wondering, yeah, I can't take counts, but I'm just wondering how many people have seen this proof, which is simple. I think everybody should see this proof. I should say that, you know, this study of determinantal representations of polynomials is a huge study in algebra. Of course, they are more restricted in the way they want to represent polynomials as determinants. But I talked to many, and they are not, you know, typically are not familiar with this very basic result, but you can always do it. Okay, so let me forget this and go to the proof. And when you have to prove anything about formulas, almost the automatic reaction is, yeah, let's do it by induction. And yeah, that's how you do it, in fact. So F is the, you know, it's the formula. It's either the sum of two subformulas or the product, right? And if you have a formula for a matrix capturing G and a matrix capturing H as determinants, it's very simple to say, ah, that's easy. I mean, I'll just create my matrix for F this way and compute the determinant, and that will be the, you know, the determinant of F. It's just a product. So it's exactly what we want to happen. So that seems easy. So that's a good start. Let's do addition. And then you look at it and you look at it and you have no idea what to do. I mean, yeah, I mean, I'm sure that if you've never seen it, you wouldn't know what to do. I mean, it's not trivial that anything would work. Okay, so here's you know, one great idea. You strengthen the inductive assumption. And how do you strengthen it? You strengthen it to demand that in all your representations, all your matrices, you want it to have ones on the subdiagonal and zeros below it. You just demand it. You want all your matrices to have this property. So assume we have it in G and assume we have it in M. And if we make this construction, it's still true that the you know, determinant of this matrix is a product of the two, and we are almost done. It just doesn't have this structure we want. We want ones along all the subdiagonal. But if you put a 1 here, you know, it still works. So we are fine with multiplication under this strongest inductive assumption. Of course, once you introduce such a constraint, you need to check the base case. Before, when the base case, a variable will be a 1-by-1 matrix. But it is easy enough. I mean, you have a 2-by-2 matrix with 1 on the subdiagonal that you know, captures any variable. So that's also okay. So what happens with addition now? Addition becomes as simple as multiplication, essentially. So draw this matrix as before. Just the same as the right side. Right now it computes multiplication, so we are not done yet. So let's add another row and another column like this. Okay, so you see I added the row with 2 1s and added a column with 2 1s, and I put the you know, maybe I should have done some animation here. Let's see, do you see my cursor? Yeah, you see my cursor?
Yeah, yes.
Okay, good. So, I mean, if you look at this matrix and you expand its determinant, let's say you expand it according to the first column, you have to take either this one or this one. And what you see immediately is that if you take this one, you will have to take this one, and you'll have to take this, and you have to take this, and you have to take this. So this will contribute 1, forget signs, and you will just get the determinant of MH. And on the other hand, if you take this guy, then you will have to take this and this and this, and this will give you the determinant of G. So it's a very simple idea, which actually gives you exactly what you want. And there's only one problem. It doesn't look like the inductive assumption is preserved because we have 1 below the diagonal, and we don't have, yeah, that's one problem, but there's an immediate solution to this. You just switch these two rows and you see magically everything becomes preserving the inductive assumption, and yeah, work like magic. So it doesn't matter if you follow this. Just the message is that it's simple and clever, and anyway, proves the completeness of determinant for formulas. So questions about this?
I don't think so.
Okay. What about the permanent? So what is even VNP? Valiant defined this class. Remember, this is a class of interesting polynomials. So what's an integer? So first of all, we demand the the integer polynomial. The degree is related to n polynomially. It's in VNP if every coefficient. I mean, that's an informal definition. If every coefficient can be efficiently computable. So it's sort of analogous if you think about it to NP, where you just want to verify the different witnesses to an NP problem. Here the witnesses are defined by the monomials, and you want to know what the coefficients is. So you want, if I give you want that the following problem will be solvable in polynomial time. The analog of verification is that if I give you a monomial description of the exponents in this multivariate polynomial, there's an efficient computation of the coefficient of this monomial. Of course, there may be exponentially many monomials. We don't, that's like there are many exponentially many witnesses or solutions to an NP problem. We just care that each individual coefficient is efficiently computable. And that's if you think about any polynomial that interests you, that is sort of explicit in any way, you'll see that it satisfies this property. Yeah, that's the point I just made. And Valiant's theorem is that for any polynomial in this very large class, you can translate it efficiently to a matrix, and the permanent now of this matrix will equal the polynomial. So everything in this class reduces exactly like before via affine projections to the permanent of a matrix that's polynomial in size, polynomial in the complexity of recognizing these coefficients. I'm not going to explain this reduction. It's one of the more sophisticated reductions we know in the business of reducibility. So, but I urge you, those interested, to look at it. It's really, again, it's very clever, very, very clever. Okay, so that's as far as I'll go on this proof. But now we have completeness of determinant for VP and permanent for VNP, and now the question of separating VP and VNP reduces to separating permanent and determinant. So concretely, with our notion of reduction, what we care about is whether there is a small affine projection from permanent to determinant, right? Whether there are some good affine maps, so I call it good, if the permanent of n by n matrices after an affine transformation becomes a determinant of a k by k matrix. And the main question is, how much bigger does k have to be in order for this to work? Okay, so this is really the question of understanding the relative power of VP with respect to VNP.
Okay. Could I ask a question?
You can ask a question all the time.
Yeah, no, but what was the reason why Valiant came to the permanent actually? I mean, is there, do you have some insights into that?
No, I don't, and I think he arrived at it from, well, yeah, I'm not sure, but he was always interested in matchings. So I think he arrived, he was interested in matchings. He was naturally interested in the permanent. And I think just studying it was, his way of, I mean, he arrived at it somehow, magically. I cannot tell you. I cannot tell you the expressive power of permanent. I mean, if you look at the reduction I mentioned before, is really it looks so much like determinant. You think that everything you can do with permanent, you can do with the determinant. But these signs are really constraining. That some of you probably know that if we move to non-commutative variables, then also determinant would become complete for the analog of VNP, non-commuting variables. So it's really about the signs. How we exactly came about the, unleashing this expressive power, I cannot tell you. It's a good question. I can ask him next time I see him. So what is this, how much blow up do you need to incur in reducing the permanent to determinant? What do we know? But it turns out this question was asked long before Valiant and arithmetic complexity. Polya noticed that for 2x2 matrices, you don't need any blow up, right? I mean, you see that you can reduce permanent to determinant this way. He also proved that for 3 it doesn't work. So K of 3 is bigger than 3. So he was interested in this question without all this motivation. From Valiant's result, we know that, I mean, you can wonder whether this number is actually finite, right? But it's finite, it's most exponential, because we know that, the permanent has formulas. They are of size 2 to the n, let's say, Reiser formula, and therefore you can reduce it to determinant by the previous completeness. So it's a finite number. It's at most exponential. The best lower bound we know is by Mignon and Rassayer. It's quadratic. It's roughly n squared over 4. It's a beautiful result. I mean, it's simple. It's a really simple linear algebra, but again, very clever and motivated from algebraic complexity. So the algebraic geometry insight that the variety of determinant contains linear spaces of very local dimension. That's basically the insight. I want to say that.
Avi, can I ask you a question?
Yeah.
Sorry, a dumb one. So this bound of Kn being upper bounded by exponential in n, before Valiant's work, was this known that this can be upper bounded by exponential in n?
No, I don't think so. I mean, I don't know that anybody asked, but I don't think that it was no. Okay. I don't think so. It follows. I mean, I don't know a direct proof other than via the completeness. Of course, you can make explicit like completeness, but I want to just point out this lower bound of n squared. I mean, especially for GCT people, this is the interesting question, right? Reductions between. I'm not talking a lot about GCT in this talk simply because you'll explore it in depth. But just to say that this quadratic lower bound is beautiful, but in some sense is a trivial bound that we have to exceed because n squared is a number of variables. One has to remember it's a number of variables. And nobody has any idea how to go above n squared. And Valiant's completeness result, as I mentioned earlier, we basically says that you want to separate VP and VNP is the same question as just proving a super polynomial lower bound on K of n. And that's really the starting point of the GCT of Malmali and Sohoni, which is trying to prove such lower bounds by, first of all, stressing that the polynomials, permanent and determinant, are extremely friendly in the sense that they have lots of symmetries and in fact are characterized by their symmetries. And using symmetries and looking at the orbits of these polynomials under linear action on the variables, which is what we are allowed to do in these affine reductions, they try to find the representation theoretic obstacles for the existence of good maps if K is too small. And I'm sure some of you know much more than me about the status of where this stand in technical terms. Of course, we don't know how to prove general lower bounds, so people have been trying to prove lower bounds on restricted arithmetic formulas, and this is a very important line of work. Also in Boolean complexity, you try to do what you can, develop techniques, and I'll mention just a few. There are, of course, many more. Noam Nissan showed that if you move to non-commutative variables, then both permanent and determinant require exponential size formula. Nobody has any idea. This is 30 years old, and nobody has any idea how to prove lower bounds for the same lower bound or any super polynomial lower bound for circuits. Maybe I should mention that Pavel Hrubesh and myself extended this result to work even for formulas which have division. So even if division elimination is not an obvious thing in non-commutative circuits, anyway, you can. The same is true for formulas with division. But anyway, for circuits, forget division. We have no lower bound. That's a great challenge. I think. The non-commutative world is supposedly simpler. This proof, Nielsen's proof, is quite simple. And yeah, we have no idea what to do with circuits. I don't know why. Another beautiful result is that is a lower bound of n to the log n on formulas, now commutative formulas for permanent or determinant, which are multilinear. So of course, determinant and permanent are multilinear polynomials. We can hope that we can compute them without introducing anything that's not multilinear in the intermediate computation. But this cannot be done in polynomial size. We have this lower bound. Of course, it would be nice to get bigger lower bound, and maybe it's exponential for both. Nobody has. I mentioned that determinant has formulas of size n to the log n, but they are not multilinear. They are homogeneous, but not multilinear. So that's another great open question. And another, more recent and very sophisticated result of Gupta, Kamas, Kayal, and Saptarishi from about, I don't know, 6 years ago, looks at other restriction, looks at the depth restriction. So he wants circuits or formula that are of depth 4. So they are sums of products of sums of products. And they prove this lower bound for the determinant n to the root n. And you wonder, if you haven't seen it before, why is this number appearing there? And it turns out that via depth reduction results of Manindra Agarwal and others, you cannot improve it. There are upper bounds of the same magnitude, n to the constant times root n. So it's absolutely tight. And as in the above two results, the same lower bound holds for the permanent. It's sort of remarkable that all techniques we have for one, we want to separate permanent and determinant, but every lower bound we have for the permanent works for determinant as well. Same lower bound works for the permanent, but in the permanent case, because of the same depth reduction result, if you improve it, there we don't have a so there since we don't know a polynomial size circuit for permanent, we don't have a depth reduction like for determinant. It turns out that just improve it a little bit, any asymptotic improvement in the exponent will separate VP from VNP. And these are just depth 4 circuits. You may think that they are so restricted you can do something there. I'm sure that Niraj and all his collaborators tried very hard. And yeah, that's one avenue to separate permanent and determinant. Okay, now I'm going very slowly, in fact. So, but anyway, yeah, we'll see how much. Maybe I won't get to the end, but at least I hope you all understand. And again, questions so far? Okay, so let me continue. I want to tell you about some really important properties of the permanent that had major consequences to complexity theory and beyond. So there are two properties, and they also are shown by the determinant. The one, they are familiar, right? So let's see. One is the downward self-reducibility. If you want to compute the permanent of n by n matrices, you can compute it from several permanents of smaller matrices, and this is simply by row expansion. right? I mean, you just expand by row. It's the same for determinant. So we know that. So we can reduce to smaller matrices if we are willing to enlarge their number. So of course, if you wanted to repeat this thing, you wouldn't go very far because you'll get an exponential number of problems to solve. But at least one reduction by one is possible. So that's one observation. The second, which is a bit more sophisticated, is random self-reducibility, and this was, so observed by Beaver, Feigenbaum, Lipton, and really had major consequences. So what is this? The permanent of n by n matrices can be computed with high probability from several, from the value of several individually random matrices. Think of the field as finite. So when I say random, I simply mean uniform, uniformly chosen. So let me explain in more detail what this is, and you'll see it's familiar. The way to think about it is as follows. Suppose you have a circuit C that computes the permanent almost always. What do I mean almost always? It's correct except on a fraction, let's say 1/8n of all matrices in this n by n matrices, okay, over this field. Okay, so you have it's a familiar sort of issue in problem testing and program testing and program correction. You have maybe a program that makes some errors and you want to transform it to one that is always correct, at least with high probability on every instance. Of course, you don't know which are the matrices for which it makes an error. So here's how you recover from this. Here are all the matrices. Here's the place where the circuit makes an error and you don't know what this set is, and you want to compute the permanent of this matrix X. You don't know whether it makes an error on X or not. And what you do is the following: you interpolate. So choose a random line through X, okay? Just a random line. So pick a random Y, a random matrix Y, and then look at the line, which contains X, X plus Y, X plus 2Y, and so on. And the idea for interpolation is that you can define a univariate polynomial. Let's call it G of a parameter T. T is in the field. Okay, it's what the circuit does on the given matrix X plus Ty on the points that you see in the picture. Okay, the main thing is that this is a low degree polynomial. It's a univariate polynomial of degree n. Okay, if you have a univariate polynomial of degree n, if you can evaluate it on n plus 1 points, then you can interpolate and get the coefficients of the polynomial. And if you can get the coefficients of the polynomial, you can evaluate it at 0 and get the value at x. The observation is that every point in this line, not x, but all the others which are dependent on the random y, are individually random. So the probability they land in the bad set is 1/8n, let's say. The probability that, so probability 3/4, none of them lands in the bad set. So all of them give you the permanent, and then the interpolation will give you the permanent of x. I hope this was clear. Questions about it? It's a beautiful idea. It's a low degree multivariate polynomials can be, you can recover from errors. In particular, you can do it for the permanent. Is it clear? Okay.
No, so here you assume you have a circuit. What if I'm a bit confused? So,
well, it just well, I'll talk next slide. You'll see.
okay.
Yeah. But I just want to point out, if you think that 1/8n is too harsh a demand, you can even make it 1/3 using coding theory. Anyway, yeah. Even if your circuit makes 30% mistakes, you can recover from it in a slightly more clever way. So what is the meaning of this result? That's what KB was asking. If the permanent can be efficiently computed on most inputs, then it can be computed on all inputs. Put differently, if the permanent is hard on the worst case, right? I'm just looking at the contrapositive. It's hard in the worst case, then it's hard in the average case, right? It's the same statement. So these worst case to average case reductions are absolutely, fundamental. This works for any low degree polynomial and creates the idea of arithmetization. Because of this, what people started doing out of, just automatically since then is every Boolean function, you extend it into a function over a field. This is arithmetization. You get polynomials. And with these polynomials, you can do these wonderful things like worst case to average case reduction. And this plays a major role. I'll mention some in lower bounds de-randomization, probabilistic proofs, which moves me to the next topic, which is efficient verification, so proof systems. I'm not going to. Those who want, I recently gave talk about proof systems, mainly because of the MIP star equal RE, breakthrough, quantum interactive proofs, which surveys all of the, essentially all the proof systems that you want to know about. So it's on my website if you want. So let me summarize this very quickly, what I mean by efficient verification. In general, it's complete generality over mathematics. It's a situation where you have some limited verifier, skeptical, wants to learn something and interacting with a very powerful prover that can prove everything, but it cannot be trusted. And this is really the normal situation that defines NP, right? The theorems with short written proofs, basically, publishing papers about results, it captures things in NP. Somebody very clever found a proof, wrote it down, and then you can read it. That's NP, and great, so it's sound and complete. And the great insight of Babai and Goldwasser, Mikhail Rakov was coming out with an extension of this type of proof system where they let the verifier and the prover interact. Maybe the verifier asks questions and maybe tosses coins. And here you demand only that the result is sound and complete with high probability. So there is small chance that the prover will fool the verifier into believing something wrong, but the verifier can reduce this error as much as he or she wants with repetition. So tiny error. And in this interactive proof model and the extensions of it, that was extremely important the last about 25, 30 years. And here is a bunch of results. And because I'm talking about permanent determinant, I want to say that it's absolutely critical that permanent was understood. This downwards and random self-reduction of permanence, these properties exist. There was an avalanche of results. Understanding proof systems evolved from in a span of a few months really. And Nissan understanding that the permanent has a proof system with two provers. I should say, permanent, as I mentioned, is not likely to be in NP. It's above NP. So we don't expect a normal written proof for the permanent. So that the fact that it has proof at all of any nature is sort of stunning. And I'll show you in the next slide roughly a sketch of why that is. So shortly after it was understood to be an IP, that's what I show you. And this led to these great understandings of characterizations of IP, SP space, of multiple prover interactive proofs as non-deterministic exponential time, and led eventually to the famous PCP theorem and all its implications, which are beyond this talk. Now let me have one slide about how the ideas we discussed of downwards and random self-reducibility play in this proof. Okay. So this sort of the idea is about compressing instances in the following sense. We saw just before that we can compute one permanent, maybe if we don't trust the circuit we have or whoever is computing it for us, for many random ones. And now we'll see how you can verify many, we'll see how you can verify many permanent claims from one random input. Okay, this is the instance compression. So here is a picture. Like before, we have all matrices. And we have a bunch of matrices there, let's say K matrices. And somebody claims, some prover claims, let's say that this is a permanent of the first, that's a permanent of the second, right? So it gives us some value A1 to AK. And we don't trust it, right? And we are not going to verify this directly. We are just going to reduce this set of claims, which can be large, I mean, let's say n claims, into one. So that, you know, if we are convinced of that one, we'll be convinced of all of them. And that's an amazing thing. It's sort of magic that you can do that. And here's how this magic works. It's, again, interpolation, basically. So you pick another random, now a random point, x1 to xk was given, pick a random point, xk plus 1, and you can pick a unique, I mean, that's by interpolation, you can choose a unique curve that goes through all of them. And now you give this curve to, you know, the prover. As before, we can write it as a polynomial of low degree in one parameter, t, and which asks for what's the permanent of point t on this curve. And yeah, we ask the prover to give us the the permanent on this curve as a function of t. That's you know, it's a univariate polynomial. It can give us all the coefficients of this polynomial. So the first thing we do is just check that, you know, the value of this given polynomial is what the prover was claiming for the first k, and the reduction is now, so we check it. That's a basic consistency check. And the reduction is that now we are picking a random point on the curve, maybe the rth point, and verify somehow, maybe recursively or in any way, verify the permanent of the value of the permanent of xr, which we know what it should be from that g of t, g of r. So we reduced. So why does it work? Because you know, if it's a low degree polynomial, if the prover was trying to cheat us anywhere, like in one of the first k points, it would have to give wrong values all over the place, and we will catch it if we could verify recursively. We catch it with high probability. So it's a magic reduction from verifying many claims to verifying one claim, and this plays in this. Yeah, that's what I said, and this plays in the IP proof of the permanent. So we are, how do they prove that? Yeah, how can a prover convince a verifier of the value of a permanent, and where we assume that permanent has no written proof? Well, it's a sequence of reductions just like that. Here's the interaction. You know, what the verifier really wants to know a permanent of a particular matrix Zn, and the prover gives a value, and we don't trust the prover. So what do? Well, we can expand by row expansion. We can get it, reduce it to a bunch of slightly smaller numbers. So that you know, will not do, because we have now many claims and we cannot recurse. But using what I just showed you, you can compress all these, you know, n by n minus 1 by n minus 1 matrices into one, and we get you know, another z n plus n minus 1, which captures, you know, all these claims. So we can reduce it and then reduce it again. So we go through this interaction, keep reducing the input size. By the time we get to a 1 by 1 permanent, we can compute it by ourselves. And the key thing is that with high probability, if the value we know about AI is correct, then the value we know about AI plus 1 is correct by the reduction of the previous slide. So it's an amazingly powerful result. This, of course, in the context of interaction, in the interactive proofs. Questions about this? It's an absolutely fundamental result and plays, of course, in lots of other interactive proof results. And these two properties are used very heavily.
So what happens if you were to do this with the determinant? Not that
it would work, but you won't need a prover because I mean everything would work as is,
No,
but yeah, it works exactly the same. Exactly the same. Okay, so how are we doing this time? Okay, it's almost an hour. Yeah, I probably have another 15 minutes, so it's that's good, KB.
Yeah.
Okay, so let me move. Yeah, roughly. Talk about Boolean functions. So I mentioned these classes in the beginning. I have counting classes. So now I'm back to Boolean computation. We want to count something like what? Here are natural counting problems. Count the number of satisfying assignments of a Boolean formula, counting the number of, let's say, k-clicks in a graph, Hamiltonian cycles in a graph, perfect matchings in a graph, number of linear extensions of a poset, number of spanning trees of a graph, and so on. Now, what is common and what is not common between these different problems? Well, one way to distinguish them is to look at the complexity of the search or decision problem regarding the find a satisfying assignment, find a click, Hamilton, and so on. And there is a sharp dichotomy. The ones on the top are NP-hard, and the ones in the bottom are polynomial time problems. So Valiant suggested, just making a class of counting problems, and it's very natural. I mean, certainly all of them are in NP, so you can define, given an NP machine, a counting problem, count how many paths are accepting. So that's a definition of Sharpie, and it certainly captures all these counting problems above. And the question is now, which are going to be complete? So we are seeking which are complete problems. So the first three are complete. And in fact, if you take any NP complete problem and look at its counting version, it will be Sharpie complete. It's really easy to see by the same reduction. And the real amazing insight of Valiant was that also counting perfect matching, which is a permanent problem, is Sharpie complete. So this sort of amazing. I mean, you would expect that the same dichotomy between will continue from the search and decision to counting, but it's not. Some easy problems in P, their counting version become Sharpie hard, and so that was done. It turns out that also counting linear extensions is Sharpie. But counting spanning trees, it's by sort of Kirchhoff, you can reduce it to the determinant. So somehow this is easy. It's not complete. So Sharpie complete problems, as I mentioned before, capture many important counting problems all over the place. And on the other hand, there are some few that are easy, and all these easy are reducible to determinant. I mentioned spanning trees, and also a very important thing in statistical physics is that for planar graphs, counting perfect matchings is reducible to determinant, so it's easy. So in the Boolean case, permanent and determinant play in some sense a similar role. Moving to quantum computing and how the power of determinant is related. So we have this, we have probabilistic computation, we have quantum computing, which is, of course, at least the search for building quantum computers, whether it can be done and whether we can protect against it in cryptography, and whether, all these things are billions spent on this effort. We know that, quantum is at least as powerful as classical randomness, and we want to understand by how much. And the basic result that really, I mean, some vague sense was articulated already by Feynman, by the different paths model, or basically says that anything in BQP, anything you can efficiently compute with a quantum computer, can be done by a reduction to determinant. sorry, to permanent, to Sharpie, to the permanent. Okay, so permanent is an upper bound, it's way below, say, p-space, which would be the obvious simulation. So somehow it plays a role there. Of course, we know about Shor's algorithm that somehow finds a problem that we don't know is in BPP. In fact, we think it shouldn't be for cryptography's sake. And so these questions about whether we can build the quantum computers, the jury is out yet, despite the huge investments. I mean, the best computers can factor maybe numbers of 2 digits, and maybe not all of them so far. Of course, there are huge technological advances in error correction, quantum error correction, and so on, so which would be essential. But I want to go back to this analogy that I made in the beginning, which is sort of really curious. So I mentioned that this wave function. So let me say that in physics there are 2 types of particles. They are called fermions and bosons, and the fermions more or less capture this kind of particles that occur in sort of physical matter as we know it, and bosons are more responsible for things like photons and transforming forces. And this is not an explanation, these are just buzzwords. But the technical interest here is the following. So they come into computational complexity. And one way they came, so I mentioned that if you have n-independent particles, if they are fermions, then the wave function behaves like the determinant of the appropriate matrix of amplitudes. And similarly for bosons and the permanent. And Valiant, some of you know, was very interested in, well, as I mentioned, in counting problems, and he found an ingenious model, which is called holographic algorithms, which can solve efficiently the counting problems I mentioned, spanning trees and planar matchings, but many others, or maybe not many, but some others, efficiently by reduction to the determinant, by very clever reduction to the determinant. And then some quantum physics people found that this model of holographic algorithm can be captured by quantum computers in which you restrict the operations in a way that's consistent to just using fermions. I'm not explaining this, but one can build a restriction of the BQP model in which you use only quantum operations that are consistent with the particles being fermions, and you get exactly the holographic algorithms. So these are all reducible. So there is a subclass of quantum algorithms which is not more powerful than, in fact, than the determinant. On the other hand, if you want to use bosons, then Aronson and Arkhipov developed a sort of model based on bosons, based on light, really, right? Light interference of light. I mean, it's also a submodel of the quantum computing model, and this is something that can be implemented. And it cannot quite compute the permanent, but it can solve some sampling problem that is defined by the permanent. So it seems like it does. We don't know that it's a harder problem, the sampling problem, but it looks harder. And so the basic question I want to leave you with in this physics blurb or physics page is this. I mean, we believe that permanent is much harder than determinant to compute. And nevertheless, nature seems to know what to do with bosons just as well as it knows what to do with fermions. So what's going on there? I mean, is it really computing it? Is it computing some approximation? Is it maybe the wrong model? I don't know. I mean, it's really curious. Some people looked at this, but yeah, I don't think that there is any understanding exactly of what happened. When you model them, the physicists are happy to tell you the wave function is a permanent and leave it at that, not the complex. I mean, complexity is just now entering physics, I think, in an important way. Let me talk a few minutes about another problem, which is the approximation of permanence. This will be just for non-negative matrices, because for general matrices, it's an NP-complete problem. So what do we want to do? We said that counting, so computing the permanent of even 0-1 matrices is a sharply hard problem, so we don't expect to do it. But what about getting it within a factor of 2, or within a factor of 1 plus epsilon? And there's a major result of Jerome Sinclair and Vigoda that this can be done. There's a 1 plus epsilon approximation. It's a probabilistic algorithm that will give you the permanent within 1 plus epsilon. As I said, it's a very important result. The way it is proved is via this general MCMC techniques, Monte Carlo Markov chain technique, which comes from physics, but with lots of interactions with computer science and analysis of this. I mean, these are computer scientists. And by today, we know such approximation algorithms, probabilistic approximation algorithms for many sharply hard problems. So what I want to ask is, yeah, okay, that's a probabilistic algorithm, and I love the randomization. What about deterministic algorithm? So here's the best we know, basically. I give you a non-negative matrix. What's the deterministic complexity of approximating it? How well can you approximate it? And it seems much more pathetic. In this paper, we show that in deterministic polynomial time, you can compute the permanent up to a factor e to the n, e to the exponential. Even this is not trivial. I mean, n factorial is trivial, but not e to the n. And I want to say something about what goes into this. One thing that goes into this is this solution to the van der Waals conjecture that if the matrix happens to be doubly stochastic, then the permanent is between 1 and e to the minus n. It's the same e to the minus n that appears in the result. So it's in the case the input happen to be doubly stochastic, you know how to bound it. You just say 1, for example. That would be a good approximation. But if it's not doubly stochastic, and there comes a new algorithm that reduces, at least a strongly polynomial algorithm here that makes any matrix into a doubly stochastic matrix. What do I mean makes? Scales it to a doubly stochastic matrix. I mean that you pre and post multiply your matrix with diagonal matrices. In other words, you multiply rows and columns by constants, and you get a doubly stochastic or arbitrarily close to doubly stochastic matrix, and then you can apply the above bound. Of course, because this reduction of scaling, multiplying by constants, is affects the permanent in easily predictable way, then you can reduce. You basically have a reduction. So this is matrix scaling. Let me mention that this result of e to the n was improved a little bit to 2 to the n in a clever way. And the major open question here is, can a deterministic algorithm do better than exponential in n? I think it's a great open question. But back to the matrix scaling point, something that is very relevant to what, this project that you are all involved in, is that this reduction or this matrix scaling algorithm was extended to a non-commutative setting in this operator scaling work with Gar, Gurwitz, and Oliveira, and then extended in many more works, some by some people that you're probably sitting there in collaboration, and many other people to geodesic convex algorithms. These are algorithms that sort of do what Euclidean convex algorithms do, but in the more general setting of Riemannian manifolds. And there are many connections to lots of areas of math, and I'll just flesh out. I mean, so you see how rich these these connections are. Again, these are talks I've given that on this subject many times. I'm not going to get to any of this, but just to mention that this operator scaling, which was motivated really by the topic I'm going to end with in the next couple of slides, by polynomial identity testing, so motivated by separating permanent determinant, led to lots of other things. It didn't lead to what we wanted, but led to lots of other things. And all these areas listed here and these problems listed here are both related to this quest and are related to each other, sometimes in new ways, by this work. And I'm sure this work will feature in many other talks that you are listening to. So the last thing I want to mention is this polynomial identity testing problem, and which somehow connects the Boolean and arithmetic world that I talked about. It's motivated by, in many ways, it's motivated by program testing. If you want to test algebraic programs that use additions and multiplications, you are wondering whether somebody specified that you can compute, you should compute something, and then somebody implements. They don't look the same, right? But they are computing the same polynomial. That's the kind of thing you'd like to verify, whether they are identically the same. That's one motivation for testing polynomial identities, doing it efficiently. Another is that just algebraic identities occur all over, mathematics, and many. And so Van der Monde proved this one. I mean, and it's not hard to do it by induction, but in general, if I gave you an conjectural identity, how can you do it efficiently? That's a general problem that algebraists are encountering. Of course, the obvious method of expanding, I mean, these are polynomials. You can check that their coefficients are the same, but they're exponentially many terms, so you cannot do that. So how do you do that? The general problem, I give you a polynomial, whether it is identically zero, and this is a famous polynomial identity testing, which I'm sure you all know about. And it has a very simple probabilistic algorithm, which is efficient. You want to know whether it's zero, you have a circuit for it, so you can evaluate it on random inputs. Oops, I think my battery is running out. Give me a second. I'll probably, let me not let it happen. Yeah. Okay. Sorry about that. I didn't want it to die. There's a simple algorithm that just plugs random inputs to the polynomial, and of course, if the polynomial is identically zero, you always get zero. Otherwise, you'll miss a variety with very high probability. So the main question is: so we have a fast probabilistic algorithm. Is there a deterministic algorithm for this problem? It's a de-randomization question. That's one way to think about it. And besides the motivations I gave you, an amazing motivation, which ties to the subject of this talk, came about 20 years ago by Cabanes and Impagliazzo, which says the following: if this problem, just this problem, happens to have a deterministic polynomial time algorithm, then you have separated VP from VMP. You have separated permanent from determinant. Those who haven't seen it, it's sort of shocking, right? I mean, what is this statement? It says that if you give me an algorithm, for a problem, so you prove that some problem is easy, then you have proved then that another problem, the permanent problem, is hard. The connection is not clear. It's not so difficult, but let me stress again. It uses in a clever way the downward and random self-reducibility of the permanent and the diagonalization argument. Yes, I suggest you look at it. It's not really complicated with a basic knowledge of complexity theoretic tools. And what I want to stress is that this, for me, is a very viable approach to separating permanent and determinant. And in fact, it's this attempt that led us to operator scaling, to these geodesic algorithms, and it's very much connected with the GCT program, even though sort of originally they seem like different approaches to the problem. They turn out to hinge greatly on efficient algorithms for invariant theoretic problems, and yeah, and there's a lot that I'm sure you'll explore, this semester. Okay, so let me end by my usual advertisement to those who want to know much more about some of these topics and many other topics in computational complexity and theoretical computer science. If you like this a really cool cover of a book, you can buy it, but otherwise it's you can just really download it from my website. So yeah, that's it. Thanks.
Yeah, lovely talk, Avi, as always. Yeah. So are there any questions for Avi?
Let me try to see you all. Okay.
Questions? No.
Questions?
Nobody? No.
So, do you think Boolean circuit low bounds be possible via the arithmetic circuits?
It's a good question. There's a general belief, which I think is well founded, that arithmetic circuit lower bounds are easier because you have a lot of tools that are not available in the Boolean case. You have all of algebra, and the arithmetic world is constrained. There are relations that don't hold there, right? I mean, in Boolean complexity, x squared equals x, and this is not true in the arithmetic world. And you can study variants like non-commutative variables and multilinear circuits and so on. There are sort of there's more structure and more paths for understanding, for making progress. We didn't get far on arithmetic lower bounds either. I mean, the most general, the strongest lower bound for general circuits is just n log d for polynomials of degree d. On the other hand, to your question, I don't know any reduction. I mean, I don't know that if we separate tomorrow VP and VNP, we will know anything about P and NP. Malmali believes what?
So more like some smaller classes, say like there is this constant depth TC0 versus constant depth arithmetic circuits like brief and date.
Yeah, so there for constant depth circuits, the situation up to about yesterday looked different, right? Up to about a couple of weeks ago, looks different because we had no way of proving general constant depth lower bound in the arithmetic world, and we have known them for a long time in the Boolean world. But Shrikant and Nutan and Sebastian, fixed it, and now we stand on the same level in both of them. We have, yeah, it's an amazingly beautiful work. I'm sure many of you have seen it. Yeah. More questions?
Arkadev? Yeah, I thought he wanted. He unmuted.
No.
Okay.
Well, I have a question, but yeah, again, it's a dumb question, which is, if I, so you said that to get a polynomial time, polysize algorithm for the determinant, would be interesting. It's n to the log n.
Formula.
Sorry, formula. Yeah. So is there interesting classes of matrices for which something better is known, like some non-trivial classes of matrices?
I don't think so.
Do you have a conjecture?
I don't know of any natural. There is a beautiful result of Shrikant Srinivasan, and I'm forgetting who else, which goes in the other direction. So he wants simpler matrices or simpler polynomials, right? That are as hard as determinant. They also will require, I mean, whose complexity is the same as determinant, maybe n to the log n. And he proves that certain sure polynomials, so these are generalizations of, like van der Monde matrices, only with, different exponents, things that seem closer to symmetric polynomials than to determinant, are as hard as determinant. So that goes in the other direction. I don't know of any natural class that of matrices for which you would have a yeah. So you would think, I used to think, in fact, that of course van der Monde, the van der Monde determinant has a small formula, right? It's a product. But if you change the exponents, and I actually worked on that, I tried to prove that sort of determinants are easy, and I failed. And this sort of explains this failure. Some of them are as hard as determinant.
I see.
You keep saying dumb questions and you ask fantastic questions, so maybe you should omit the beginning.
There any more questions? So then let's thank Avi then for a wonderful talk as always. Yeah, thank you, Avi.
Thank you. Yeah, great
yes,
to be here. Yeah.
Yes, and we'll like to get your slides and
I'll send
put it
you.
up on the
I will. Yeah. Just send me a reminder. Yeah, I will.
positively. Yeah.
All right.
Thank you. Thank you.
Bye-bye.
So much. Bye. Take care.